Good morning students. Welcome back to online classes of VLSI design. In today's class we are going to see our next topic, that is pull up to pull down ratio for an nMOS inverter which is driven by one or more pass transistors. Okay. So this is also one of the important topic. Before moving to this topic, we'll just revise what was the last topic we have discussed. So that was the topic where we have seen the nMOS inverter and we have seen the ratio of pull up to pull down for an nMOS inverter which is driven by another nMOS inverter. So what we have seen in the last class, we are using two nMOS inverters and the two nMOS inverters are driven by each other back to back. Yes or no? So that was last topic that we have discussed, and the ratio that we have got for pull up to pull down ratio for nMOS inverter which is driven by another nMOS inverter, that is 4:1 or 4:1. Correct? So in last class we have seen that an nMOS inverter is driven by one more nMOS inverter. In today's class we are seeing the topic where your nMOS inverter is driven by another nMOS inverter, but they are connected with your pass transistors. Means the pass transistors are driving your voltage. So your nMOS inverter is driven through one or more transistor, one or more pass transistors. Correct? So before moving to that one, we'll see what was the nMOS inverter. What is the basic requirement for your nMOS inverter? So it is the basic requirement for producing the complete range of your logical circuits. So without your inverter we are unable to get your all logic circuits. Okay, the pack of your logic circuits. So the requirement for preparing or for the generation of your nMOS inverter was you require a transistor as well as a load resistor. But load resistor consumes more space on your fabrication chip. So instead of that one, what we are using one more transistor which is in the depletion mode. Means we are using a depletion mode transistor, and the depletion mode transistor is called, or the depletion mode device is called as your pull up transistor, and the enhancement mode device is called as your pull down transistor. That is how we have seen your last topic. So in today's class we will be seeing the pull up to pull down ratio for an nMOS inverter which is driven through one or more pass transistors. So before moving to the topic, so first we will see what is the definition or what is meant by a pass transistor. So pass transistor is nothing but an isolated nature of the gate which allows the MOS transistor to be used as switches in series. So whenever you are connecting your transistors, one of the application of your MOS transistor is that it will be acting like as a switch. Correct? So what is the nature, the isolated nature of the gate that allows the MOS transistor to be used as switches when it is connected in series. So this is the application of your MOS transistor which is called as pass transistor, by which switching logic arrays are formed. We are switching, we are moving. So this is the pass transistors that will be using for getting the ratio when two inverters are connected. Okay, they are connected. These pass transistors will be connected in series. If I consider an example, if three pass transistors are connected in series and VDD is the input, and if you consider a variable X as an output, then the output that I will be getting over here, that will be A into B into C, and A, B, C are the input voltages that we are getting from the gate. Okay, so the gate, the isolated nature of the gate that allows the MOS transistor to be used as switches. Okay, so this will be used as switches and they are connected in series. This is how your pass transistor will be working. Okay, so we'll see into the topic, that is when your nMOS inverter is driven through one or more pass transistors. Okay, first see the consideration, how we are arranged this whole circuit. We are having these two pass transistors. Go back to the last video, see there how we have found the ratio of nMOS inverter that is driven by one more nMOS inverter. Means directly they are driven by inverter 1 output of inverter 1 is given as input for the inverter 2. But here what you are doing, series of pass transistors, they are connected between your inverter 1 as well as the inverter 2. So this is the arrangement that we are giving for getting the ratio of your pull up to pull down transistors, correct? So in this arrangement, in which the input to the inverter 2 comes from the output of the inverter 1, but that passes through one or more pass transistors, which is as shown in the figure, one or more nMOS transistor, and these transistors are nothing but your pass transistors. They are kept in series, and this is the application of your MOS transistor, one of the application of your MOS transistor. Now the connection of the pass transistor is in series, which will degrade the logic level 1 into inverter 2, so that the output will not be proper logic 0 level. See ma, what we are saying, what is the condition or the operation of your inverter? Whenever you are giving the input as 1, the output should be 0. Yes or no? If you are giving the 0 as the input, you will be getting 1 as the output, correct? So here also we are having, in last class also, in finding the pull up to pull down ratio of nMOS inverter, which is driven by one more nMOS inverter, there also we are having the same condition. But here we are using the pass transistor between the two inverters. The thing that that is important is that we will be having a threshold voltage in your pass transistors. So whenever, suppose if I am giving an example, I am giving a 0 as the input at point A. So what will be the output that you will be getting? 1. If I am giving 0 as the input, you will be getting the 1 output. Directly that 1 is given to the inverter 2 at point C? No, because we have to subtract the threshold voltage which is present in your pass transistors. So that's the reason we have given this statement that whenever the logic level 0 is given into the inverter 2, so that the output will not be proper logic 0, because that has to be subtracted. We will be getting some subtracted value, that is nothing but VDD minus VTP, that will be obtained. That VTP is nothing but threshold voltage of your pass transistors. So that is how we will be seeing the operation, and we will be getting the ratio for these two transistors. Okay, so we'll say first we'll be considering the critical condition. In this critical condition, when at the point A, what you see here at the point A is at 0 volts. Okay, the point A is at the 0 volts and B is thus at VDD. Of course, whenever you are giving the 0 as the input, the output will be 1. So 1 is nothing but your VDD. But the voltage into the inverter 2 at the point C is now reduced from VDD by the threshold voltage of the series pass transistors. Correct or not? I hope now this sentence is very clear to your paper, because we are having some threshold voltage in this pass transistors. This VDD cannot be directly given to the input for the inverter 2. We have to subtract the threshold voltage of your pass transistors from the output of the inverter 1. Correct ma? So therefore the input voltage to the inverter 2 at the point C here will be V inverter 2 is equals to, means V into inverter 2's input is equals to VDD minus VTP. VDD is the output of from your inverter 1 minus VTP is the threshold voltage which is present in the pass transistors or series pass transistors. Clear? Now let us consider the inverter 1. First we are considering the inverter 1, this part. Okay, the inverter 1 with the input of VDD. What we are giving the input as? VDD. If the input is at VDD, then the pull down transistor T2 is conducting. Okay, but with a low voltage across it. What it is conducting? Transistor T2 is conducting with a low voltage across it. Therefore, it will be in the resistive region, and that resistive region is considered or represented as R1. Okay, that the figure I will be showing in the next page. Okay, so meanwhile the pull up transistor T1 is in the saturation. Whenever T2 is in the conducting region, if it is in the resistive region, of course your transistor T1 will be in the saturation region, and that is represented as the current source. See, this is the current source. I am representing it as in the current source. Why? What I have said, T2 is conducting, means this is the T2 that will be conducting. So it is in the saturation region, T1 is in the saturation region and T2 is in the which region? Enhancement mode. Okay, so this is the resistor RL. I am considering the down one. This is the pull down transistor, and in the depletion mode, which is in the saturation region, that is represented as the current source. You have to make the figure in such a way that transistor T1 is represented as current source and transistor T2 is represented in your load resistor. So T2 is in the conducting stage, so therefore it will be in the resistive region, and that is represented as R1. Meanwhile, your pull-up transistor T1 is in the saturation region, and that will be represented as your current source, this figure. So this T1 is in the depletion mode and your RL, this T2 is in your enhancement mode. This is for the inverter 1 with the input voltage VDD. Seema, this is I am considering only this part, and this part is given as figure of this one. Okay, now we are having, this is the first inverter. Go back to the last video or assume that one. What is the inverter we are having? We are having a transistor and a load resistor. This is the transistor T1, okay, which is in the saturation region, and the T2 is in the conducting region, therefore it is in the resistive region. I am giving it as just R1 as a representation. Okay, for the inverter 1, and the input for the inverter 1 will be VDD. So for the enhancement mode, so this is the reason IDS and VDS relationship is very important. That is the basic relationship which completely flows throughout the chapter. Okay, so from the first IDS and VDS relationship in non-saturation region or in the resistive region, what is the formula? IDS is equals to K into W by L, VDD minus VT into VDS1 minus VDS1 square divided by 2, drain to source voltage, and this is your input voltage. This is the equation of your IDS VDS relationship which is in the resistive region. Okay, now we have to find the R1 value. I have said this is the R1 value. We have to find what is R is equals to V by I. Correct? Now we will be getting doubt that what is PD1? That is nothing but your pull down ratio, pull down transistor. We are considering the enhancement mode pull down transistor. So I am giving it as suffix values pull down transistor 1. Clear? So W is width and L is the length. And what is the R1 value? R is equals to V by I. So VDS1 divided by IDS. 1 by K. Just substitute the values. What is the VDS? It will be the same. IDS value will be VDS divided by IDS your K into W by L, VDD minus VT into VDS1 minus VDS1 divided by 2. What I will be doing? I will be taking the common as VDS1. So this VDS1 and the common taken VDS1, they both will be cancelled, and after simplification you will be getting the formula as 1 by K L PD1 divided by W PD1, reciprocal of that one, into 1 by VDD minus VT minus VDS divided by 2, because I have taken the VDS common over here and have cancelled by using this formula, substituting in R1 value and cancelling the VDS value. Okay, I hope you are clear up to this point. Now since VDS is very small and that is negligible here. Okay, now we are neglecting this VDS1 divided by 2. If 1 is very small, 1 divided by 2 is nothing but 0.5. So that will be negligible. So overall approximately your R1 value, the first inverter's R1 value is equals to 1 by K. As I have already said, your W by L, L by W is nothing but I am substituting it with the value Z. Okay, in last class we have seen that one. So the R1 is equals to 1 by K ZP1. This is LP1 by WP1. This is substituted or equals to Z, and that Z into PD1 of 1 by VDD minus VT, because this VDS by 2 has been neglected. So this is the equation 1, okay, of inverter 1 in enhancement mode. Now we are seeing the same inverter 1 in the depletion mode. Okay, we have to see this depletion mode now. Correct? I hope you are clear up to here. So what is the depletion mode device we are calling? Pull up transistor. Enhancement mode device will be called as pull down transistor. Now we are considering the depletion mode pull up transistor in this saturation region. So in saturation region, in your IDS VDS relationship, what we have said, in saturation region VGS value should be is equals to 0. Substitute this value in IDS equation, you will be getting this equation, and this is the formula for your saturation region. So IDS is equals to K into W by L VGS minus VT whole square by 2. Just simply you have to substitute the VGS value is equals to 0, then you will be getting this answer. This is the saturation region formula. Okay. So I'll be giving the link of that one once again. Just go through the video how you got this formula for the saturation region. So now I am considering, as this is for the inverter 1, I am giving it as IDS is equals to I1. So I1 is equals to IDS is equals to K into, this is for the pull up transistor in the depletion mode. Okay. So WPU1 divided by LPU1 minus VTD whole square divided by 2. Why? Because VGS is equals to 0. Okay, this was the condition. This is the equation 2. Now what I am doing, I am doing the product of this I1 into R1 for getting the output voltage from the inverter 1. Just go back to the figure. From this inverter 1, you have to get the output. V out is equals to, what is V is equals to I into R. We are having the value of I1 and we are also having the value of I1 and R1. So what we are doing, we have to do the product of both I1 and R1. So V out 1 is equals to I1. What is the I1 formula? K into WPU divided by LPU1 into minus VTD whole square divided by 2 into, what is the R1 value? What we have got to be 1 by K ZPD1 into 1 by VDD minus V1 or VT, sorry. So that K and this K will be, this is in the numerator, that is in the denominator. They both will be getting cancelled and the answer will be, this has substituted as ZPU1. So ZPD1 divided by ZPU1 into 1 by VDD minus VT into minus VT whole square divided by 2. So this is the equation 3, the output voltage which we have got from the inverter 1, and this has to be passed through the pass transistors and then given to your inverter 2 as the input. Correct? This is the output voltage of your inverter 1. This was up to your inverter 1. Now we have to consider your inverter 2. Same, I am here in the inverter 2 also, I am considering the transistor as the current source, and this is as it is in the resistive region, I am giving it as R2 value. Okay. Now what is IDS2? Same from the formula, IDS is equals to WPD, because it is an enhancement region, first I am considering the enhancement region, plus your VDD value here, your VDD value. See ma, this is the equation that you are getting from IDS VDS relationship, the VDD minus VT into VDS1 minus VDS1 square divided by 2. This is from the equation, correct? So wait a second. So what you are doing in the second transistor, second inverter, what is the input mark? We have to subtract the input value with the threshold value. So VDD is equals to VDD minus VTP. This I have given now, this part, inverter to here. So VDD minus VTP. So instead of VDD, what you have to substitute in the value over here? VDD minus VTP. So this is the equation that you will be getting for the inverter 2. So IDS2 is equals to K into WPD by the LPD, because you are considering for the depletion mode, that is your pull down transistor, and the input for your second inverter will be VDD. Instead of VDD, what you will be getting? VDD minus VTP. The VDD minus VTP, that is the threshold voltage of your pass transistors. Okay, so that is the condition, K into WPD divided by LPD, VDD minus VTP minus VT minus VDS by 2 into VDS. Either you multiply in this one, either you can take common over here. Okay, now what will be the value of R2? That is VDS divided by IDS2. I will be cancelling VDS2 value and VDS2 value over here. This one and this one will be cancelled, and as VDS2 is negligible, same, then you will be getting answer as R2 is equals to 1 by K ZPD 2 by into 1 by VDD minus VTP minus VT. This is the fourth equation. Same again, I2 value in the in your saturation region, you have to consider VGS is equals to 0 directly like this, This one, consider the saturation region IDS value, substitute the value of VGS is equals to 0, then you will be getting the I2 value is equals to K into 1 by ZPU2 into of minus VTD whole square divided by 2. Correct? Now substituting, again you have to do the product, as you have to get the output of the inverter 2. What you will be getting the output? V out 2 is equals to I into R. What is I2 into R2? You have to substitute the value, do the product of that one, and you will be cancelling the K values over here, and you will be getting as ZPD divided by ZPU2 of 1 by VDD minus VTP minus VT of minus VTD whole square divided by 2. This is the equation 6. I think this part has cut. This is nothing but VDD minus VTP minus VT, this one here, okay, into minus VTD whole square divided by 2. This is the equation 6. Now what you have to do, if the inverter 2 is to have the same output voltage, under this condition what you have to consider, V out 1 is equals to V out 2. In case if you are having the same output for both inverter 1 and inverter 2, what you have to do, you have to equate these two equations, means V out 1 is equals to V out 2. What is V out 1? ZPD1 into divided by ZPU1 of 1 by VDD minus VT of VTT whole square divided by 2, that is equals to ZPD2 divided by ZPU2 1 by VDD minus VTP minus VT of minus VTD whole square divided by 2. These both I will be cancelling. Okay, so what is the answer? ZPU2 divided, I have simplified. Simply I have simplified this one, ZPU2 divided by ZPD2 is equals to ZPU1 divided by ZPD1 of VTD minus this one. I am taking the reciprocal and just simplification I have done. Please do try it. It is very easy. You can easily get it. In case if you are having any doubt, please do let me know. I will clarify that one. And in my notes I have clearly given every step over there. Okay, so your value for this one, ZPU2 divided by ZPD2 is equals to ZPU1 divided by ZPD1 into VDD minus VT. This I have bringing it to numerator side, divided by VDD minus VTP minus VT. This is the equation 1. What is VTP? Threshold voltage of your pass transistors, and VT is nothing but your threshold voltage. VDD is the input voltage. Correct? Now, substituting the typical, as we have said, we have to get the ratio of this nMOS inverter which is driven through one or more pass transistor. So as to get that one, we are having some typical values that we have to substitute in that one and get the values. So what are the typical values that we are having? VDD value is equals to 1.0. Okay, and VT threshold voltage is 0.2 VDD, and the threshold voltage of your pass transistors is 0.3 VDD. Substitute these values over here. Here VDD is 1 minus threshold voltage is 0.2 divided by 1 minus 0.3 minus 0.2. Then you will be getting the answer as 0.8 divided by 0.2. Simply after simplifying, you will be getting as pull up to pull down ratio is 2 and pull up to pull down ratio of inverter 1 is 8 divided by 1. Okay, this is how you will be getting. You just simplify, and this is your assignment that you have to get me the simplification how you got these values. So from this above theory, it is clear that for an nMOS inverter, if an inverter is driven directly from the output of another inverter, then the ratio will be greater than or equals to 4 divided by 1. This ratio we have found in last class. When one nMOS inverter is driven through one more nMOS inverter, then the ratio should be equals to or greater than 4 by 1. In case if your inverter is driven through one or more transistors, one or more pass transistors, then the ratio should be equals to or greater than or equals to your 8 divided by 1. So this is how you will be getting your answer. So the pull up to pull down ratio for your nMOS inverter driven through one or more pass transistors is equals to 8 divided by 1. And if the pull up to pull down ratio for the nMOS inverter driven through one or more another inverter, then its ratio should be equals to 4 divided by 1. I hope you are clear with today's topic. Okay. In next topic we will be seeing about your CMOS inverter. This was all about your nMOS inverter. pull up to pull down ratio for your nMOS inverter driven through pass transistor or directly through one more nMOS inverter. Clear? So what is the depletion mode and enhancement mode transistor? What is that one, ma? I should give an assignment for your people, take an exam for that one also. So if your transistor is in depletion mode, then that transistor is called as your pull up. Depletion, pull down transistor. Enhancement mode, it will be a pull down transistor. Okay. Depletion mode device is always called as your pull up transistor. Enhancement mode device is always called as your pull down transistor. So I hope you are clear with today's topic and the ratios. Please do remember, you may be getting for 7 marks question or 10 marks. 4:1 the last class video, it might be getting for 5 marks. But completely your whole first chapter is very, very important. Please do practice well. In case of any doubts, please do let me know, ma. We'll end today's class up to here itself. Thank you.